We gone. So we will be talking today about homogeneous differential equations. Last time we had separable equations, and the reason why I ask you to solve some problems before coming back to class is that the first topics of this class are related to each other. So you cannot do homogeneous problems if you don't know how to do separable equations, because when you do a transformation in homogeneous problem, what you obtain is a separable equation. So it's important to do the previous stuff before coming to class. So, differential equation. A differential equation of the form m of xy dx plus n of xy dy equals 0. This is the generic form of the equation that we'll be having, and we will handle this for a couple of lectures. A differential equation of this form is said to be homogeneous if and only if the functions m of xy and n of xy are both homogeneous of the same degree. So a differential equation of the form m of xy dx plus n of xy dy equals 0 is said to be homogeneous if and only if the functions m of xy and n of xy are both homogeneous of the same degree. In this definition, there are two things that are very important: homogeneous and degree. We don't know yet what those things are, and that's why we are going to define those here. A function f of xy is homogeneous of degree n if and only if for all x, y's, this notation in mathematics means for all x, y's and t, f of xt, yt is equal to t to the power n f of xy. So that's what it means that the function is homogeneous of degree n. So if I replace in the function x and y by x times t and y times t, the value of the function gets rescaled by t to the power n. Then we say that the function is homogeneous of degree n. An example, let's say f of xy equals x squared plus y squared. For this function, f of xt, yt is equal to, this means replace x by xt and replace y by yt. So that becomes x times t squared plus y times t squared. So we go into the function and we replace x by xt, and we replace y by yt, and we compute this to see what happens if we can factor out a power of t. Here, this is x squared times t squared plus y squared times t squared. And you can see that there is a common factor, t squared, that shows up. So you can factor out t squared, and what is left is x squared plus y squared. But now you can see that this x squared plus y squared is exactly the value of the function at xy. So that's t squared times f of xy. So by definition, for any x, y, and t, we can get that f of x, t, y, t is equal to t squared times f of x, y. This means that f of x, y is homogeneous. See, in here, the degree is 2 because that is t squared. Does this make sense? That's example 1. Now let's do example 2. F of xy equals x cubed over x squared plus y squared. If we do this, for example, and then we take f of xt, yt, that means replace x by xt, so that is xt cubed over xt squared plus yt squared. When you do this, that gives you x cubed t cubed over x squared t squared plus y squared t squared. So this is what you get. And now you can see that the t's cancel, and you have f of xt yt equals t squared cancel. So this is x cubed over x squared plus y squared times t. Because t squared cancels with the t squared that is down there. You factor it out, it cancels. And now you can see that this is t f of x, y. And so you have a power of t that pulls up, that's t to the power 1. So the degree is 1 and it is homogeneous. This function is homogeneous. Of degree 1. All right. Now, any questions?
What is t squared to in that final answer?
Can you say that again?
What did you write? T is squared to what? What is that?
What line?
The second from the bottom, the last part.
Here?
Yes.
Okay, that's t cubed over t squared. It becomes t.
Okay, and then equals, what's that last part say?
T times f of xy, because this is f of xy.
Okay, so it's just t times f of xy.
Yeah, I just rewrite this because what you want to have is t to a certain power times the function that was originally there. So the whole purpose of this is to replace x and y in this formula by xt and yt and see if you can pull out a power of t and still have the original function.
Okay, thank you.
So here what we do is when we do this, we simplify t squared cancels. You have 1t that remains. You still have x cubed over x squared plus y squared. And this piece is the original function. So I just write it down times the t that was in front of it. And that gives me what I want because I needed a power of t times the original function. Therefore, we can conclude that the function is homogeneous and the degree is 1 because the power of t that popped out is 1. Here it was degree 2 because the power of t that popped out of the function here was 2. Are we good? Ethan?
Yes, sir.
All right. Okay, so if we are good with this, let me give you an example and you try and tell me if the function is homogeneous or not. So exercise f of xy equal x squared plus 1 minus y squared. Is this function homogeneous? You tell me. Do the work and tell me if you can write this as a power of t popping out and having f of xy again.
This says x squared plus 1 minus y squared.
Yes, sir.
Okay.
So what do you think? Is this an homogeneous function?
Do you want us to just unmute ourselves and say?
Yeah. What do you think when you look at it now? Is it homogeneous? Is it not?
I don't
When,
homogeneous because I couldn't cleanly factor out the t or a factor of t.
yep, that's it. You can't. So it's not homogeneous because you can't pull out a factor of t when you do that. You have f of xt, yt. This is xt squared plus 1 minus yt squared. And that is t squared x squared plus 1 minus y squared t squared. And this thing is not equal to t squared times x squared plus 1 minus y squared. It's not. Because 1 is not multiplied by t squared. Right? One is not multiplied by t squared, so you don't have it. Therefore, f of xy in this case is not homogeneous. So not all functions are homogeneous. Right? Does that make sense now? Is everybody okay with this?
I have a question real quick. Does
Yeah.
that mean that if there's a constant in the function that it won't be homogeneous?
Technically, right here, that's what this one would say.
Okay. Is there a case where if there is a constant and it's still homogeneous?
If it's a sum, it's not going to be. It's never going to be homogeneous if you have a function of x, y, and then plus something that doesn't have x or y. That's a good question, actually. And the second thing is, if you have a sum, then you better have the same powers that come in each of the terms of the sum, right? So tip for polynomials and their fractions or their ratios. For polynomials and their ratios, look for the power of each of the terms of the sum. If all the terms of the sum have the same power, then it's going to be homogeneous. If they don't have the same power, then it's not going to be homogeneous. Example, say f of xy equals xy plus x squared minus x cubed. I would say the power of this thing, look how I count the power. This is x to the power 1, y to the power 1. So the total power for this term is 2. 1 plus 1, 2. X squared, that's power 2. X cubed, that's power 3. It's not same as 2. So this thing is not going to be homogeneous. Because the power of this one is different from the power of the others. Am I making sense? Now, if you take another one, let's say I take the same thing, but I leave out the last one, then power is 1 plus 1, 2. Power of this one is 2. 2 and 2 are same, so this is going to be homogeneous. Of degree 2, because that's the power. So that's kind of a tip that you can use when you see things like that. Any questions? Okay, so that's pretty much it for homogeneous function. And why do we define them? Because they are used in the definition of homogeneous equations, which is the topic of today's lecture. So again, we say that a differential equation is homogeneous if the functions m and n are both homogeneous of the same degree. Let's look at some examples now. So let's say we have an equation that says x minus y dx plus x dy equals 0. Is this equation homogeneous or not? What would you say?
I would say that it is.
Yes.
Yeah, got that. Well, give your explanation, please.
Someone else was talking. Does someone else want to?
Yeah, someone was saying
Because they're both to the power of 1.
they're both to the power of 1, so they are both homogeneous of degree 1. Therefore, the equation is going to be homogeneous. And if you check that, you would see that if you take m of xy, that is x minus y, m of tx ty is going to be t times x minus t times y, and you factor out the t, you get x minus y, so that's t m of xy, exactly as you said. That's homogeneous of degree 1. And so n of xy, that's x, n of tx ty, that's tx, and that is t times n of xy, and again, that is t to the power 1, and these two numbers are same. And that's t to the power 1, t to the power 1 as well. Therefore, the equation is homogeneous. Now, once you establish that the equation is homogeneous, it's not over, because we're actually not interested in you telling us that the equation is homogeneous. We're interested in you solving it. So the question is, how do you solve it? And today's lectures is about a method for solving such equations when it is already established that the equation is homogeneous. How do you solve it? So that's what we do now, solving homogeneous equations. How do we solve an homogeneous equation when it is already established that the equation is homogeneous? How do we solve it? So the first step is use the substitution. Y equals u times x, where u is considered a function of x, and therefore dy is u dx plus x du. This is using the product rule to compute the derivative of u times x. That's the product rule for that. So the substitution is this, and I take the derivative of y, knowing that this is a function of x, u is a function of x, tells me dy equals u dx plus x du. And then substitute this. The equation. So you take these two things, you substitute in the equation. You replace y by ux, and you replace dy by u dx plus x du. And then simplify the obtained equation by grouping terms in dx and du separately. So once you substitute in the equation, you group the terms that have dx and you group the terms that have du separately, right? What you obtain from here, the resulting equation is, and guess what? Our previous lecture, separable. So when you follow these steps that I'm giving you, the equation that you obtain from there is a separable equation that you solve as a separable equation. So solve it as a separable equation. That's it. And at this point, if you do nothing with separable equations, you're lost, because it's a problem that's adding on top of another one, and you need to use both things to answer one question. Now, let's say example 1. The problem that we had on top of this page, x minus y dx plus x dy equals 0. And we go by that first step. It says use that substitution. So it's always going to be this same substitution, y equal ux, dy equals u dx plus x du. That's it. First step is always same, no matter what the problem is. Nothing is going to change on that first step. Second step, substitute them in the equation. So I take these two things, take y in the equation, take dy in the equation. That's it. That's what that means. So I'm going to have x minus ux dx plus x times u dx plus x du equals 0. That's it. And it'll be straightforward if you really follow the steps that I provide to you in class. There will be no mystery, right? So then you have your third step. Simplify the obtained equation by grouping terms in dx and du separately. So I take all the things that have dx and then all the things that have du separately. With dx, what do I have? I have x minus ux and then plus xu, that all times dx. That's everything that has dx. I combine them. That's what the step says. Then I take everything that has du. There's only one term. That's x times x squared du equal 0. That's it. That's the step 3. Now you can do all the algebra that you want in between here. So x minus xu plus xu, they cancel. That's x dx plus x squared du equals 0. Things cancel. And now here, And we said the equation that you obtain is a separable equation. So on that last step, you solve that separable equation. This is a separable equation. How do we solve a separable equation? First thing, we separate the variables, right? Get all the terms with dx on one side, get all the terms with u on the other side. So we're gonna do x dx equals negative x squared du, and then we separate the variables, send all the x's to this side and keep the y's, the u to the other side. So that's x dx over x squared equals negative du. Of course, when I do this here, I always say, remind yourself that when you are dividing, you're never dividing by something that is zero. So we're technically excluding x equals 0 when we divide here. And so this gives us dx over x equals negative u. The variables are separated. For a separable equation, what we do? So here we separate the variable. What we do next here?
Why did you drop the du? Like, why'd you drop the d?
That's du, not u. It can't be dropped.
Next step is to integrate, right?
Good. Next step is integrate. So right here, that's what we're going to do. We integrate both sides. So that's integral of dx over x equals negative integral of du. And so we compute that integral. Integral of dx over x, that's natural log of absolute value of x. And actually, I could just add natural log of c as a constant. And then integral of du is u, so that's negative u. And so u, the last thing we always do in this problem when we solve, after solving, we always have this step, this one, this is return u equals y over x into the solution. So I didn't write that here, but that's the last step always you have here. The last step of the problem, because here you have u, but the problem was not given to you in terms of u. It was in terms of xy. So when you do that, you return that here. You got ln of cx, I put these together, equals minus y over x, or y equals negative x natural log of cx. Right. All right, and so that's what you would do. Now you remember that before we got here, we said x was not 0. But initially, nobody in the problem said that x was not 0. And now, in the final answer that we got here, we see that technically the solution x equals 0 is also excluded. It's not part of this. X equals 0 is not a solution here. So we need to go back and check this solution that we excluded. Check this solution that we excluded to see if it's also a solution. So here, check x equals 0 for solution. How do you check that? Well, you say x is 0, dx is also 0, and this is x equals 0 as a function. The function x equals 0, right? For all y's. That's a function, not just a point. So dx, the derivative is 0 if the value of the function is always 0. And if we bring that back in here, into the equation. X is 0, dx is 0, this thing is 0, right? X is 0, the whole thing is 0. So you have 0 plus 0 equals 0. So yes, it is a solution. 0 plus 0 equals 0. So x equals 0 is a solution. So the final answer should be y equals minus x natural log of cx, or x equals 0. So the two things form the general solution of this problem. Any questions? Now, while I keep the example on the board, let me ask you to solve another example. Is anyone still writing this down?
I actually have a question, but I'm not still writing.
Okay, so what's your question, sir?
I don't know if this is like a sensible question to ask, but like, if while we're doing this and we find our solution, how can we be sure that the function or group of functions we find is the only solution? Does that make sense?
No, I'm missing something.
Like, I don't even know if like this just makes sense, but like I just don't know if like could there be a function that this process misses that would also be a solution to the differential equation, I guess.
The only case is this, when you have to divide by something that could be 0. If you don't check it, then you might miss that solution in the end. Other than that, there's no other solution that you're going to be able to find that is not part of this. Why is that? Because the general theory here is just trying to say, okay, just try to find a u such that the function y will be u times x. Technically, you have no requirements on u. It's any function. And any function can actually be written as u times x. Just divide it by x and then multiply by x, right?
Mm-hmm.
So if there is a solution, it can definitely be written in this form.
Okay, that makes sense.
Does it make, okay?
Yes.
And now we just say, okay, let us start by that. And we started by that and we found all possible solutions. So anything that can solve this equation, gotta be this or that.
Thank you.
You're welcome. Any other question? Now let me give you another example and keep here the steps and you try to solve it, okay? So I'm just gonna put that example right here in this small box. Exercise. Solve. That'll be x plus y dx plus x dy equals 0. And give you 5 minutes on this. It's exactly same as what we just did, just that some signs change, right? And then you follow the same steps that we have here. Any good news? Anyone with something to share?
Isn't it not homogeneous?
What?
Isn't this not homogeneous?
It is homogeneous, and what you need is to
Okay.
the steps in solving. I don't need you to show that it's homogeneous. Here are the steps 1, 2, 3, 4, and then 5 there. So tell me what you get in the first step. I mean, second step, because first step is obvious. It's the same thing you write down. For this problem, what will be the first step? You have x plus y dx plus x dy equals 0. Step 1, y equals ux dy equals x du plus u dx. So what's the second step? What do we get in the second step?
You substitute, so you get x plus ux times dx plus x times u dx plus x du.
Correct. And then the third step says, combine the things in dx and the things in du. So what we get?
Get x plus 2 ux dx plus x squared du equals 0.
That's correct. So x plus ux, that's 2ux plus x squared du equals 0. Correct. And then you simplify. So you are going to step 4 to solve the obtained separable equation. So how you do that here, you get out the x, factor it out, 1 plus 2u dx plus x squared du equals 0. You can see that it's a separable equation. So you get all the x's on one side. So that's x dx over x squared equals minus du over 1 plus 2u. So send this to the right, divide the whole thing by 1 plus 2u, and then divide by x squared. You get that. That's separation of variable. So again, here you separate the variables. And then after separating the variables, what we do?
Integrate.
Integrate. That's it. And I do believe with these things, it's just need to remember that at this step, this is what I do. You can actually say it and write it down, even if you can't do it, but you need to know that that's what to do at this point, right? So here becomes integral of dx over x, because x over x squared is 1 over x, equals negative integral of du over 1 plus 2u. Now you integrate both sides. The integral here is going to be ln absolute value of x. Technically, see this, and often I will do this in the integration. Put the constant of integration inside because of natural log. Why? Because natural log of x plus natural log of c is equal to natural log of x times c. So often when I integrate this, I'll just write this. It makes things simple. It makes things simpler for me. Equals, and then I integrate this one. You can use u substitution on this. So that is 1 plus 2u equals v, dv equals 2 du. So that is negative integral of dv over 2v, which is minus 1/2 natural log of v. Which is minus 1/2 natural log of 1 plus 2u. And to make my life easier, I can do many things actually. So I get negative 2 natural log of absolute value of x times c equals natural log of 1 plus 2u. I just multiply both sides by minus 2. And now I can exponentiate. So please follow this carefully. Here I'm doing this actually because I want to use it to explain something that will show up several times in this class later. So we take exponential on both sides. Now, exponential of natural log is just what is inside there. So that's 1 plus 2u. A exponential of negative a number, this is where your problem is. And if you forget about what we are doing, then you might have issues with some of your problems when we start a new topic. So this is going to be exponential of natural log of absolute value of xc raised to the power minus 2. These are the properties of exponentials and natural logs. So if you have a number in front of natural log, that number can go into natural log as the power of what is inside. That is why this becomes exponential natural log of xc to the power minus 2. And those who refuse to listen to this when I'm explaining, I asked that question 5 times and they will turn this into minus 2xc. Right? Which is wrong. And I will keep repeating and they will keep doing the same thing, right? So there's only one right way to do it. Take that number from here, put it inside natural log as power, and now it turns into this. An exponential of natural log is what is inside, and that's why this is 1 over xc, and I can just write that like this, xc squared, because negative power is 1 over, equals 1 plus 2u. And now you can replace on the last step as we do, 5, return y equals u, return u equals y over x. And so that gives us 1 over x squared c squared equals 1 plus 2 y over x. So that's how you go about that. So now you can stop your answer right here and you can continue simplifying if you want, but this is good enough for me. Now, one thing is missing here. What is it? What is missing here as solution? Can you tell me?
Take the x equals 0.
The x equals 0 thing, because we excluded it. When we divided here by x squared, we had a condition that x is not 0. So now we got to come back and check x equals 0 as function. Dx is also 0 in this case. And so, and the equation is x plus y dx plus x dy equals 0. And we can check that x is 0, so that's 0 plus y dx is 0 plus x 0 dy equals 0. And this is true always, no matter what y is. Therefore, x equals 0 is a solution. In conclusion then, our answer is one over x squared c squared equals 1 plus 2 y over x, or x equals 0. That's it.
All right, so like, say we had this type of problem on the test. Do
Yeah.
we have to make sure we check for the x equals 0 every time?
Yes, sir, if that is the thing that you divided by.
Okay.
So, no idea, was this someone just kicked out, or it seems somebody was kicked out? Any other questions? Yeah, he was kicked out, James. So, right, if there's no question, let me provide you one more example. So, let's say dy over dx equals y over x plus x over y. And again, I always say, please, when we do this in class, follow. When we say, take 5 minutes to do this, try to do it too. And then you see where you have a problem. When the instructions are still in front of you, follow the steps. If you don't, then you are creating issues for yourself, right? Because when the time comes, you say, man, I didn't learn this thing because they didn't explain it to me. But when they ask you to do that, you didn't do because you thought it was simple. It is simple when somebody else is doing it. When the instructor is doing it, it's always obvious until you start doing it by yourself. So please follow the steps on this one. And I'm going to put down those steps again. So here are the steps. On the side here, I'm going to put that, right? I'm guessing I will put the problem on top of the steps. And that's the problem below here, right? So that's the problem. And here are the steps. You have 5 minutes, and then I'll solve it. And again, remember when I say just solve, follow the instructions because I already know that the equation is homogeneous. I'm not asking you to show that it is homogeneous, just saying solve, follow the steps.
I have a question.
Yeah,
So can a DX cancel?
what?
Can a DX cancel? Like I got
Never.
never. Okay.
Because if it does, it means it's disappearing from your equation. And so the equation We're not supposed to have that. It's really very rare to have a problem like that. Now remember, in this case, it's written as dy over dx. So you got to send dx to the right side, right? So that would be that's where you start this one. All right. Is anyone with something we can share? Because I have 5 minutes left. I need to show you the answers.
I have a solution.
Okay, let's go through your steps. First step.
Okay, so the first thing I did was I multiplied everything by dx.
All right, that's what we already have.
I also multiplied everything by, I did it a little differently than that picture. I multiplied everything by xy.
You can do that too, but it's not necessary. It's just getting a long work for no reason.
My solution is probably going to be a little too long.
Yeah, that's the thing. You don't need to do it. So
That's
because y over x, x over y, this is u and 1 over u. So, but when you can multiply and then you head into more trouble, just follow that step. The next step is y equals u equals dy equal. You don't transform anything.
Okay.
Mhm.
Sorry, I was way overthinking it.
Yeah, it will make it a little more difficult, just, but you still get the right answer.
Okay, so first we would substitute
Ux and dy is
u dx plus x du.
great. And now you put that in the equation. Dy is this. You will see that as this is just going straight. So y is ux. Ux over x is u plus x over ux. That's 1 over u dx. See?
Yeah, I really don't know what I was thinking. That's my bad. Thank you.
But when you do this, it's good to do this when we are still in the learning process, because instead of the exam, you already have that mistake. You already know you will do that. So, and you go fast. And that's what I like about doing these things in class, because you learn on it. And when the time comes when you need it, you are quick at it because you already know. And now the next thing we do is take the x's together, take the dx's together and the du together, right? So these are dx. So we send this other thing that is dx together there. And we keep the du here. So that's x du equals. And when this comes here, this is u. It goes as minus u. It cancels the u that is here.
Well, I have a question.
Yes, sir.
How do we get that u plus 1 over u?
Y over x is u.
Oh, x is u. Oh, okay.
Mhm.
Now I see.
And then x over y is 1 over y over x, which is u. Are we good? Now, again, in this place, you got u dx. It goes to that thing with dx. And you got u minus u, so they cancel. So you're left with dx over u. This is what the equation turns into. Straightforward. And now the third step is solve the obtained separable equation, which is u du equals dx over x. That's what we get. Why? Because u goes here, it becomes times. Dx goes over here, it becomes 1 over. And now, next thing is you integrate. Integral of u du equals integral of dx over x. Then you integrate each of them. That's 1/2 u squared equals, and this is natural log of x times c. Remember, I just told you that I could just do this, right? Anytime I have natural log, I can put the constant inside to save myself some lines. And then you bring, this was 4, and then in 5, you return u here. So 1/2, this is u is y over x squared equals natural log of x times c, or y squared equals 2x squared natural log of xc. And again here, we don't need to worry in this case about dividing by x here. Why? Who will tell me why we don't need to worry about that?
Because x equals 0.
Mm,
Or the x equals 0 thing. Is that why?
Yeah, I said, why don't we have to worry about that x equals 0 as in the other problems?
Or is it because there's nowhere where we divided by x?
No, we did. We divided here. But why shouldn't we worry?
Is it because there was never a place where we canceled an x by dividing? Like we never had something like x squared over x cubed?
Not really.
Well, final answer, y squared equals 2x squared ln of xc. 0 can be a solution. Like x equals 0 can be a solution in that.
It still can be. It still can be. And he's right in saying we didn't divide anywhere, but the answer is hiding plain sight here. Look at where the problem starts. Can you have x equals 0 in this problem?
No, it's in the very beginning.
The very beginning, right? It's a denominator. So at the very beginning, you can't even look at x equals 0 as a point even. Secondly, right here, the problem starts as dy over dx, this, which is technically actually y prime, right? So technically giving you the problem in this form means that we are looking for a function of x. Moreover, in this one, you're dividing by x in the original problem, so x can be 0. So we shouldn't worry here about looking at the separate case, x equals 0. Does that make sense?
Yes.
All right, that's the only reason why in this problem we are not going to look for that, and we will claim that our final answer is this. Y squared is 2x squared natural log of x. That's it, and I think the time is over. You have any questions, feel free to ask. Otherwise, we'll meet next time. And I am stopping right now the